Hi, thanks Alex. I'm Kimmy, and I'm going to tell you about my favorite application of detector technology. That's particle physics, where we learn about the smallest building blocks of the universe. So far, we've learned about how detectors can be used to translate light into information. The detectors I'm going to be talking about are going to be we're going to get information from other particles, not just photons. So we want to learn about the smallest particles in the universe. So how are we going to make detectors that can do this? And what information can we possibly get from them? To answer this question, let's go back to what we learned about the eye and cameras. They can have varying resolution depending on how many cells are in your eye or how many pixels are on your CCD. But in general, we can't see sizes much smaller than, say, an insect. But what if we want to see something smaller, like the rods and cone cells in the eye? These are really small, about 1/100th the thickness of a piece of paper. We're getting to almost unfathomable sizes here. But luckily, the microscope has allowed us to see these by giving us a greater resolution, so we can make observations about cells and learn about them. But in order to understand our universe, we have to go even smaller, because everything around us is made of atoms and molecules. For example, water, H2O, is 2 hydrogen atoms and 1 oxygen atom bound together to form the water molecule. Now, we can sort of imagine how small a cell is, 1/100th the thickness of a piece of paper, but the atom is so small that we're going to have to make another analogy. So imagine a huge football stadium, and imagine a tiny fruit fly and how small it is in comparison. The ratio of the size of the fruit fly to the length of the football field is about 1 in 10,000. That's actually the same ratio as your cells to you, like your rods and cones. So if you were the size of a football field, your cells would be 10,000 times smaller, like the size of a fruit fly. And atoms are another 10,000 times smaller than even cells. But we can ask, is there something smaller than the atom? If you've studied a little chemistry, you know the answer is yes. The atom isn't just this solid sphere that I've shown in the cartoons so far. It's actually made of a nucleus at its center, surrounded by electrons, which orbit the nucleus. The electrons are the particles of electricity, actually. And it turns out that the nucleus is the ratio between the size of the nucleus and the size of the atom is the same as the ratio as the size of the fruit fly to the size of the football field. So the nucleus is so tiny, and the nucleus is made of protons and neutrons. So the so-called subatomic particles that make up everything around you are then just protons, neutrons, and electrons. I find it so amazing to think about the diversity of matter and life on Earth that's made of just these 3 units. From diamonds to fruit, to you and your eyes and your cells, everything is just protons, neutrons, and electrons. Now, you may have heard of protons, neutrons, and electrons, but in particle physics, we want to go even smaller. Basically, we want to know, is there anything smaller inside the proton? Clearly, we're getting to ridiculously small sizes. And just like when we went to the small size of the cell, we need a new technology. Because so far, all the detectors we've talked about have relied on the reflection of light off an object and into our detector. So say we have some green photons, some green waves of light are hitting our green tree and scattering off onto, maybe into our eye so we can see the tree. But the problem is that protons are so small that the wavelength of light is huge in comparison to them. So the light just passes right by like it's not even there. So the way that we detect the smallest particles in the universe is through the Large Hadron Collider and detectors like it. particle physicists from around the world came together to build this huge underground tunnel in Geneva, Switzerland. It's called the Large Hadron Collider. Inside, we accelerate protons to nearly the speed of light, and we smash them into each other. We smash them open to see what's inside. So the yellow circle on the map is indicating where the tunnel is located underground. Notice how huge it is, as you can see this International Geneva Airport in the image, which pales in comparison to the size of the collider, which is 17 miles around. So that means every time the protons go zooming around the Large Hadron Collider, they travel 17 miles. But remember, they're traveling at close to the speed of light. So the trip only takes them 1/10,000th of a second. So what do we learn when we collide the particles together and smash them open? Tons of particles come zooming out. Electrons, photons, and even more exotic particles that had never before been observed. So what's going on? Well, we figure out what's going on, and we learn about the smallest particles that mankind has ever observed with the largest detectors that mankind has ever built. This is one of the detectors at the Large Hadron Collider. It's made of a bunch of different separate detectors, a lot of which work like the CCDs we talked about so far. Notice how huge this detector is. There's a person standing next to it who looks so tiny in comparison. They're standing next to a 5-story tall detector. So, what have we learned when we make precise measurements of the particles that come out of this collision? We've learned 2 important things. First, that protons are indeed made up of smaller subunits. Protons and neutrons are made of these small units called quarks. I've labeled them U and D in the cartoon. The second important thing we learned is that new particles are created. But how is this so? There wasn't electrons or photons or exotic particles inside the proton. The answer lies in Einstein's famous equation, E = mc². The total input energy of the fast-moving protons that we collide together is equal to the total mass of the particles that are created times the speed of light squared. So Einstein's equation is telling us, it's describing the collision by saying that the 2 protons come in with a total energy E, and that energy is equal to the total mass, when you add up all the masses of the particles that come out, times the speed of light squared. So we haven't created something out of nothing. We've just converted energy from one form into another. And this is the essence of what makes particle physics so different than any other type of science. We create new matter and convert energy into mass. So as physicists, as particle physicists, we want to learn about the building blocks of the universe. We do this by colliding protons together at nearly the speed of light, smashing them open and seeing what comes out. And the way we detect what comes out is with special detectors. So this is an image of the inside of the detector, the huge 5-story tall detector that you saw previously. So each panel you see here in the detector is a silicon tracker, which is just a CCD. Each of the CCDs contains thousands of pixels, which detect the presence or absence of a particle. And altogether, the detector has 75 million pixels. So that means that every time a particle comes flying out of this collision, it gets detected at one of the pixels, and its position is therefore determined to the width of a human hair. This super accurate determination of the position allows us to trace back exactly what happened and how the particles were able to be created from the energy of the collision. The other main goals of the detectors, besides just determining the position, is determining the speed and the mass of the particles. This is done by detectors called calorimeters. The main idea behind calorimeters is the resistance of a particle to move through a material. So to see what we mean, I have a video of a bullet zooming through ballistics gel. So at the beginning of the video, the bullet's moving really, really fast. And as it goes through the material, it slows down and eventually stops, leaving a shower of destruction in its wake. Therefore, the gel contains all the information about the bullet at the end of the process. This is just the way calorimeters work. Instead of a bullet, we have a particle that came out from the collision. So the particle goes zooming through the calorimeter. And instead of ballistics gel, we have metal slabs, which slow down the particle. And just like the shower of destruction that was created from the bullet, we have a shower of particles. And so the farther the particles travel through the metal slabs, the more speed they must have had, and the more energy they must have had. So the position of the particles is determined by detectors that work just like CCD detectors that are placed between the metal slabs. This way, if a particle makes it only to the first slab, it will get detected there, and it must have not had very much energy because it didn't make it very far. Whereas a particle that gets detected maybe at the end of the calorimeter, it must have had so much energy because it made it all the way through those metal slabs. So by counting how many particles are given at each detector, this lets us know how fast the particle is moving. So this is a side view diagram of the detector, the huge 5-story tall detector that you saw. And we've talked about the trackers, which measure the position, the calorimeters, which measure the energy and the speed of the particle. And then we have a few other types of detectors, along with magnets, which give us all the information that we can put together and figure out exactly what happened and how the energy of the collision was converted into mass. So we've learned by using these detectors how an explosion of particles can give us the laws of particle physics, the laws of the universe at the smallest scale. So thinking back to atoms and molecules, chemistry experiments allowed us to make the periodic table of the elements, which classifies all the atoms of everything around you. Analogously, the standard model of particle physics classifies all the particles that make up atoms themselves. The standard model contains the particles as well as the rules that the universe follows at the smallest scales. So we have the quarks, like the up and down quark, which are inside all protons and neutrons inside all atoms. And then we have the electron, which is orbiting the nucleus of all atoms. And then we have the photons, which is a force particle, the photon we talked about earlier. The latest big discovery in particle physics occurred at the Large Hadron Collider in 2012, and that was discovery of a Higgs boson. This discovery was so huge that it led to the 2013 Nobel Prize in Physics. The Higgs boson is so important to the Standard Model because the Higgs bosons acted at the beginning of the universe to give all the other particles their mass, and it determined how the force particles interact with the matter particles. So basically, the Higgs bosons are the reasons we're here today. For me, the most mesmerizing part of particle physics is its unwavering truth across space and time. Experiments we do here today on Earth give us insight into the laws of physics that have been true since just moments after the Big Bang at the very beginning, and give us information about how particles act at super high energies like those orbiting around the center of a black hole. So we have different types of detectors, and basically we're turning information from particles through our detector into information that we can learn about the world around us. So whether our detector is an eye, or a CCD detector, or a huge particle detector, the possibilities are endless because detectors allow us to make observations of our world and do science like we never would have been able to do before. So what lies in the future of detector technology, and what are we going to observe next?